So here's a video about finding quadratic rules for sequences. You've hopefully watched my previous video about finding the rule, where you have a simple sequence that goes up by a set amount every time, and you find a rule that's usually nth term equals something times n plus or minus something. So here's a more complicated sequence, and it's complicated because it doesn't go up by a set amount every time. So it's 1, 7, 17, 31, 49, 71. So we've got to find a general rule for that and test it. So putting that into a table, when n is 1, the nth term is 1. When n is 2, the nth term is 7, because the second term is 7. And then when n is 3, the nth term is 17, because the third term is 17. So it's just a table that has n equals 1, 2, 3, 4, 5, 6, 7 onwards, and then the term that fits that position in the sequence. Then if we think about the differences between terms, I'm going to calculate the first difference, and then I'm going to calculate something called the second difference. But let's look at the first difference first. So the differences between the terms go 6, 10, 14, 18, 22. So 7 minus 1 is 6, 17 minus 10 minus 7 is 10, 31 minus 17 is 14. So it's not a fixed difference every time. But then when we find the differences between the differences, which I'm calling the second differences, we find 10 minus 6 is 4, 14 minus 10 is 4. It's 4 every time. So although the first differences weren't the same number every time, as they had been for previous simple sequences we looked at, the second differences actually are constant. And that tells us something important. That tells us that the general rule for the sequence takes the form, there we are, an squared plus bn plus c. So it's a quadratic rule instead of a linear rule. So instead of being something n plus or minus something, it's something n squared plus something n and something on the end. So generally speaking, we can find a rule for this that's a quadratic expression, an squared plus bn plus c, and we need to find out what a, b, and c are so that we know what the rule is. Well, we can do this by plugging in some known values. So for example, when n is 1 here, so I plugged in n equals 1, then the nth term, the first term, is also 1. So the nth term is 1 when n is 1. Plugging that all in, we get 1 equals a times 1 squared plus b times 1 plus c, which just reduces to 1 equals a plus b plus c. Now what about the next one? Well, the next one is when n equals 2, and then the nth term is 7. So if we plug all that in to this, we get 7 equals a times 2 squared plus b times 2 plus c, which we can simplify a bit to 7 equals 4a plus 2b plus c. And then we can do that with the third one. So when n equals 3, the nth term equals 17. So we can plug in 17 here for the nth term and 3 here for n. So we get 17 equals a times 3 squared plus b times 3 plus c, which simplifies to 17 equals 9a plus 3b plus c. So basically we've got a system of 3 equations in 3 unknown things. Now you're familiar with simultaneous equations where you've got 2 equations in 2 unknowns and you kind of eliminate things to figure out what the x and the y are. You can do the same thing with 3 equations in 3 unknowns. Now you'll notice that all of these have c in them, the same amount of c, just one c, and that's going to be very helpful to us because if we label these equations 1, 2, and 3, then we can do equation 2 minus equation 1. So 7 minus 1 is going to give us 6. 4a minus a is going to give us 3a. 2b minus b is going to give us b. And then the c's are going to disappear. C minus c is going to disappear. So we'll just get 6 equals 3a plus b. Well, we could do the same thing with equation 3, take away equation 2. And that would give us 17 minus 7 is 10, 9a minus 4a is 5a, 3b minus 2b is b, and the c's disappear. And there it is. So we've now reduced a system of 3 equations in 3 unknowns to a system of 2 equations in 2 unknowns. And you should already know how to solve that. It's just basic simultaneous equations. And here we go. So I'm labeling those 4 and 5. Just going to move the whole thing up a bit to give myself more space, but keep the table there. No expense spared on the animation here. Going up a bit more quickly there, and nearly there, getting rid of those. There we are. So we've got 2 equations in 2 unknowns, and luckily the b's are the same in both of those. So we can just do equation 5 minus equation 4. 10 minus 6 is 4. 5a minus 3a is 2a, and then the b minus b disappears. So we've eliminated the b's now and reduced it to 4 is equal to 2a. And of course we can easily find out what a is from that. Divide both sides by 2. So 2 is equal to a equals 2 is the answer for a. Now that we know what a is, we can plug it back into, let's say, equation 4, although we could equally well do it in equation 5, but we'll plug it back into equation 4 to try and find out what b is. So equation 4 was 6 equals 3a plus b. Now that we know that a equals 2, we can say 6 equals 6 plus b. Take away 6 from both sides to get 0 equal to b. So that's what b is. B equals 0. Now that we know what a and b are, we can go all the way back to the beginning and plug those into one of our original equations. So that's what I'm going to do next. Again, I'm just going to move these away to give myself some space. And I'm going to substitute in equation 1, which, if you remember, was 1 equals a plus b plus c. So plugging a equals 2 and b equals 0 into that, we get 1 equals 2 plus 0 plus c, or in other words, 1 equals 2 plus c. Take away the 2 from both sides to get the c on its own, and we've got minus 1 is equal to c. So that's what c is. C is minus 1. And now that we know a, b, and c, we can plug them all back into this to get the rule. So the rule is that the nth term equals 2n squared plus 0n minus 1. 0n's just nothing, so we can get rid of that and say the rule is nth term equals 2n squared minus 1. Okay, well, the question said to test that rule, and in the IB exam, when they ask you to test a rule like this, the marks tend to be for testing it beyond the range of the ones that we've already got. So to try and figure out, say, the 7th one, to test our rule that way. So we expect the 7th term to be 2 times 7 squared minus 1, according to that rule. And that works out to be 97. And then, indeed, if you carry on the second differences as 4 and the first differences as 4 more each time, so you get the next difference should be 26, and 71 plus 26 is 97. So that all ties in with our difference table. So in the IB exam, if you're asked to make a rule and test it, always test it by going one more beyond the one or two more beyond the values that you've already got. Okay, so now one for you to try. And the question is, find a general rule for the nth term of the sequence 54, 59, 70, 87, 110, 139. Test your rule. So just pause the screen now and pause the video now. I keep saying pause the screen. Pause the video now and try and do that, and then start it up again when you think you've got it and you want to check. Okay, so hopefully you did that, and here come the answers. So there's the rule in a table. So n equals 1, 2, 3, 4, 5, 6, 7, 8, whatever, along the top, just for the first term, the second term, the third term. And then the actual terms themselves in the next row, nth term is 54, 59, 70, 87, 110, 139. So looking at the differences. First difference, 5, 11, 17, 23, 29. So not a constant difference. So it's not going to be a simple rule like nth term equals something n plus or minus something. Second difference is 6 every time. So that tells us it's going to be a quadratic rule. If it had gone down to the third differences being constant, then it would have been a rule with a power of 3 in. And if it had gone down to the fourth differences, then it would have been a rule with a power of 4 in. But hopefully on your exam, it will just go as far as second differences and a quadratic rule. So since the second differences are the same, we can fit a quadratic rule to the data. So the rule takes the form that the nth term equals an squared plus bn plus c. So again, we can stick in particular nth terms and particular values of n to try and figure out what the a, b, and c are. So when n equals 1, we've got the first term, which is 54. So the nth term is 54, and 54 equals a plus b plus c, because it's a times 1 squared plus b times 1 plus c on the end. So that's our equation 1. Equation 2, it's going to be the second term, 59. So 59 equals 4a plus 2b plus c. 4 because it's 2 squared, 2 because n equals 2, and an odd c on the end. And then for the third term equals 70, so it's going to be 70 equals a times 3 squared plus b times 3 plus c on the end. So in other words, 70 equals 9a plus 3b plus c. Okay, so we've got 3 equations in 3 unknowns, and they've all got the same c in them. So if we subtract equations, the c's will disappear. So I'm going to do equation 2 minus equation 1 to get 59 minus 54 is 5, 4a minus a is 3a, and 2b minus b is b, and then c minus c disappears. Then I'm going to do equation 3 minus equation 2 to get that. 70 minus 59 is 11, 9a minus 4a is 5a, 3b minus b, 2b is b, and c minus c disappears. By the way, if you're sharp-eyed, you'll notice that all of the a, b, and c coefficients are the same as last time. So we had a, b, c here for the first equation last time. We had 4, 2, and 1 there last time. We had 9, 3, and 1 there last time as well. That's because these n numbers are all the same. It's always 1, 2, 3, 4, 5, 6, 7, 8 there, and we're doing exactly the same thing as before with them. Okay, so we've now reduced a system of 3 equations in 3 unknowns to a smaller system of 2 equations in 2 unknowns, and luckily the b's are the same. So if we do equation 5 minus equation 4, the b's should disappear. So let's do that. Equation 5 minus equation 4 gives 11 minus 5 is 6, 5a minus 3a is 2a, so 6 equals 2a, which gives us that a equals 3. And now that we know that a equals 3, we can plug it back into equation 4. So equation 4 was 5 equals 3a plus b. Now that we know a is 3, we can plug that 3 back in there and get a 9. So 5 equals 9 plus b. Take away the 9 from both sides to get minus 4 is equal to b. So that's what b is. B is minus 4. Now that we know the a and the b, we can go all the way back to the start and plug them back into equation 1. So 54 equals a plus b plus c becomes 54 equals 3 minus 4 plus c. Well, 3 minus 4 is minus 1, so that becomes 54 equals minus 1 plus c. Add 1 to both sides to get 55 equals c. So that's what c is. C equals 55, and then our rule that the nth term equals an squared plus bn plus c becomes nth term equals 3n squared minus 4n plus 55. So that's the rule, and if we test it, we get 174 there. If you plug 7 in for the 7th term, you get it coming to 174, and that ties in with what we expect from a difference table. So that all works when we check it.